Welcome to ICUDemy, the educational channel of the Critical Care Society of Kenya. In this session, we will explore the concept of time constant in respiratory mechanics. When pressure is applied to the respiratory system, the change in volume follows an exponential curve. The time constant determines the time taken for the lung volume that is passively inflated or deflated to change by 63% of the current value. It is expressed by the following relationship, where V sub t is the volume at time t, V sub I is the initial volume, E is the Euler's number, and tau is the time constant. Time constant can be calculated during inspiration or expiration. Mathematically, one time constant is equal to the product of resistance and compliance. Now, let's visualize how the time constant affects lung filling and emptying. The green curve represents lung inflation. Notice how the lungs fill rapidly at first, then slow down as they approach full capacity. The red curve represents lung deflation. Similarly, the lungs empty quickly at the start, but slow down as expiration progresses. Each time constant represents a significant change in lung volume. After 1 tau, the lung has filled by 63%. After 2 tau, it has reached 86%. By 3 tau, it's at 95%. After 4 tau, nearly full at 98%. During expiration, after 1 tau, 37% of lung volume remains. After 2 tau, this drops to 14%. By 3 tau, only 5% remains. After 4 tau, less than 2% of the initial volume is left. In summary, it takes between 3 and 5 time constants for the lungs to fill or empty almost completely. Note that the expiratory time constant is independent of the ventilator settings, since expiration is a passive process. Let's explore how the inspiratory and expiratory compliance affect the breath timing. To demonstrate the difference between inspiratory and expiratory time constants, we begin by plotting the compliance curves for inspiration and expiration. The blue curve represents inspiration, where compliance is lower. The green curve represents expiration, where compliance is higher. During inspiration, the lungs offer more resistance to expansion, requiring greater pressure to achieve the same volume, hence lower compliance. During expiration, compliance increases, making lung deflation easier at lower pressures, hence higher compliance. See how compliance changes at different lung volumes and also between the inspiratory and expiratory phases. In summary, a higher compliance and resistance in the expiratory phase means a longer time constant, explaining why expiration takes a longer time than inspiration even in normal physiologic states. For an intubated patient with normal lungs, the expiratory time constant is between 0.5 and 0.7 seconds. In the next session, we shall demonstrate the effect of various states of altered lung mechanics on the expiratory time constant. In this scenario, the expiratory flow curve demonstrates that the time allocated for expiration matches the expiratory time constant, an expected finding in normal lungs. A similar pattern may appear in conditions like recruitable acute respiratory distress syndrome, pneumonia, or mixed etiologies, where a pseudo-normal time constant may be observed. Moving on to the next scenario, the time allocated for expiration is shorter than 3 time constants, which is insufficient for complete exhalation, a pattern seen in obstructive lung disease. Lastly, in this case, the time allocated for expiration is longer than 5 time constants, which is excessive for complete exhalation, a pattern typically seen in restrictive lung disease. What is the take-home message? The time constant is the product of resistance and compliance. In normal lungs, one time constant is between 0.5 and 0.7 seconds. In obstructive lung disease, one time constant is greater than 0.7 seconds. In restrictive lung disease, one time constant is less than 0.5 seconds. In mixed etiology disease, one time constant may be pseudonormal. Thanks for watching.